Hey, grade 12s. Welcome back from spring break to your first video lesson back. Thought I would just share my face here because it's been a little while, and I thought maybe it would be nice to get a little sense of normalcy, to be able to see that I'm still here. We're still doing our thing. We're still going to continue on to learn our physics that we were doing beforehand. So I hope your spring break was good. I didn't do a whole lot. Stuck around home, started some basement renovations, didn't get that far on them, but was able to relax, and we are back now. So a couple things I want to touch on first. I posted on the classroom, I posted a student progress check-in on a Google form, and 23 of you did it. So that's great. I would think there's 29 of you, so I'm missing 6 of them. So if you are one of those 6, if you could please do that, it's just a good way for me to be able to keep track of, how this communication thing is going and the fact that we're actually checking in. So if I haven't heard from you yet, I need you to do that for me. And then it's also got some really valuable information in there that I've been able to kind of tweak some of my lessons here in order to be able to help you all a little bit more during this kind of tricky time. I hope you're all doing well. If you want to let me know what you got up to on your spring break, I know it probably wasn't a whole bunch. Maybe you were able to, maybe you were working. You can shoot me an email, or you can put a comment on the YouTube video or on the Google Classroom. And I'm going to continue to do Thursday meetups on Google Meets. So no pressure, but if you are struggling, it would be a really great time to be able to ask me to help you out with some physics questions in real time, and also just to be able to see each other's face again, and kind of, maybe some other people from the classroom log in too. We can have a little chat. Anyways, enough of that. Let's get on with our lesson here. Oh, sorry, the other thing that I wanted to update on is I'll be updating your marks online. I've got a couple of people asking about some homework check problems. I fixed those. Don't worry about that. Like I said, those were just kind of when we were in class, those are just for me to keep track. Now that we're not in class, it's a little bit more difficult. So I've kind of just scratched that. Make sure that you get the ogres handed in. And when I get the third ogre marked and back to you and in my system, I'll update the marks. And then, like I had mentioned, I'm planning on doing some sort of assessment because we do have midterm report cards coming up soon. Stay tuned for that. Just make sure that you're checking the Google Classroom, okay? So I'm going to turn this off, and I'm going to turn on my PowerPoint because we are going to do a problem of the day. And today is April 7th, which I have April 6th written here on my PowerPoint, so I got to fix that. April 7th. And April 7th is no housework day. So if you've been having mom and dad or whoever's at home on your case for trying to get some housework done today, you can let them know that nationally, or I don't know, maybe globally, I didn't actually check if it was international or not, it is technically no housework day. So kick back and relax, and maybe let that room stay messy for one more day. So there you go. This might be a little bit tricky, so I want you to pause after I finish reading it because this might be kind of tough. This is throwback to what we were doing before spring break. So when we were talking about two objects colliding with each other and that conservation of momentum between them. So two objects are moving towards one another, collide, and they rebound straight back in the direction that they came from. So it makes our problem a little bit easier. We don't have two dimensions going on here. Object 1 has a mass of 5 kilograms and is moving 2.0 meters per second before the collision, and then rebounds backwards with a velocity of 3 meters per second. So make sure you're drawing this out. Object 2 is a mass of 7 kilograms and was moving 3 meters per second in the opposite direction. What is its velocity? So what is the velocity of object 2 after the collision? Now is your chance to pause. And if you paused, hopefully you're back now and you have worked on the question on your own. And if you did, maybe it took you a little while, but that's okay. That's the beauty of this. Here is my answer I got. Compare your answer to mine. So I have that initially the number 1 is moving in the positive direction and number 2 is moving in the opposite direction, in the negative direction. And And we just plug in all the information that the question gave us. So M1 was 5, V1I was +2, M2 is 7, V2I, so the initial velocity of object 2, was -3, is in the opposite direction. And then after the collision, M1, which was 5, is moving in the -3 meters per second direction. And then plus M2, which is 7, and then we're trying to find the velocity of object 2 finally. So if I do all that, 5 times 2 gives me 10, 7 times -3 gives me -21, 5 times -3 gives you -15. So 10 minus 21, -11, and then add 15, divide by 7, you should get positive 0.57 meters per second. Okay, positive 0.5 meters, 57 meters per second. Looking back at my question here, that should be positive 0.6 for sig figs. So that's my bad. Okay. So then if we are now ready, we can, I'm going to make this full screen. Oh, it only full screens over here. Bear with me. I need to move this over here. For some reason, this will only full screen on my one monitor. And it's not blurry. All right. Okay. Present this window now. We are moving on to work today, which is kind of funny because today is no housework day, but we do have to talk about work in physics today. So what is work in the physics world? Okay, well, work inside of our physics definition is, where's my mic? I don't want to cover my mic up. Is the result of the force acting on an object to cause a displacement. So it's the result of forces acting on an object that will cause a displacement in that object. It can also be thought of as a transfer of energy. Okay, work can be a transfer of energy. We're moving an object by applying a force to it. So think about this example right here. A golfer uses a club and gets a stationary golf ball moving when he or she hits the ball, obviously. The club does work on the golf ball as it strikes the ball. Energy leaves that club, right? The club had some kinetic energy stored within it, and it leaves that club and enters into the ball. This is a transfer of energy between these two objects. So what we say then, by definition, is that the club did work on the ball. The club did work on the ball. How do we calculate work? Well, based on our definition we have up here, the force acting on an object to cause a displacement, work is simply the force causing the displacement, the force multiplied by the displacement. So let's do what we normally hear, write out what everything is. That is the force. This is the displacement. And right here is the work. Now, work is one of those ones, again, where our unit is kind of very not creative. We, initially at least, one of the ones that we use is newtons times meter, right? We have the force and we have the displacement. So our units could either be Newton meters, or our other option is a transfer of energy. Quick right now, you can pause, tell me what the unit of energy is. It's a joule. So a joule is 1 unit of energy. So that is, since work can be thought of as a transfer of energy, we can actually measure it in joules. Now, this is very important right here. Note, work is a scalar. It does not have anything to do with direction. We don't have to consider a direction. This actually comes from the dot product. If we are taking calculus, you might have learned about the dot product already, but that might not be in your course. But it's the dot product between the force and the displacement. And what ends up happening is we end up getting a scalar value. it's a scalar product. A dot product is the same as a scalar product. We end up getting a scalar. Beyond what we need to know, for right now, just trust me when I say that work is a scalar. It does not have a direction. So it's nice. We don't have to give a direction. We just give it as either a positive amount of energy or a negative amount of energy. Now, a little side note here is to remember that force is the one that's causing the displacement. So it's always going to be in the same direction as the displacement anyways, okay? So we don't need to give a direction. Let's do a couple examples. In our notes here, what do we got? We got 2 examples, 3 examples. Let's do 3 examples. It's been a little while since we've done some notes. Example number 1, a box with a mass of 10 kilograms falls straight down a distance of 2 meters. How much work is done by gravity on this box? The box is falling. Okay, the box is 10 kilograms. That's our mass. And I'm going to say that just for simplicity's sake, because we're falling, I'm going to say downwards is the positive direction. So let's use our formula. Work is equal to the force multiplied by the displacement. Now remember, force here, in this case, because it's falling, the force is going to be equal to the force due to gravity, right? So this is actually going to be Fg. Let's replace Fg with what we've learned in the past. Fg has always been equal to mg. So now we have work is equal to mg delta d. Hopefully, I don't know if you guys can see that or not. Should move this too. Mg delta d. And now let's write in all of our values. So m is 10. G is 9.8, but it's 9.8 down, which I've already said was positive. So positive 9.8. And the displacement is also down, so it's positive 2.00. And what we get is we get 10 times 9.8, that's 98 times 2 should give us a positive 196 joules. That is our work. So we don't need to give a direction. But what I do want to mention is it is important to note that this is a positive value. What a positive value is telling us is that this object gained energy. Remember, we said that work is a transfer of energy. So it's either going to gain energy or it's going to lose energy. Well, this one gained energy, right? As an object falls, it's accelerating downwards. It's gaining more kinetic energy. It's moving faster. So that was a situation where work was causing an increase in the amount of energy in the object. Pretty straightforward question. Let's move on to question number 2, example number 2. A child pulls a rope attached to a toy with 10 newtons of force, 20 degrees above the horizontal. The toy moves 6 meters, and this really, I mean, it's moving 6 meters horizontally, right? They're not moving it on the angle. So I maybe should have included that in the question. Horizontally. How much work was done on this toy? So, pretty interesting looking toy, just a little box. Okay. And the child pulls on it like so with 10 newtons of force at 20 degrees above the horizontal. So because we've only got movement in the x direction, right? Our displacement's only going to be in the x direction. We want to find the force in the x direction as well. So because delta D is going to be in the x direction, we need to also have F be in the x direction too. So we're trying to find Fx. That means that work is also going to be in that same direction. So work is equal to Fx delta D. Or delta D, if you want to, you could say delta dx. How do I find the x component of this? Remember, this is SOHCAHTOA. This is the adjacent, so it's going to be 10 cos 20. So work is equal to 10 cos 20 degrees times 6 meters, right? That's what our delta dx was. If I plug in 10 cos 20 into my calculator, I should get 9.396926208, and then multiply that by 6. And we should get something like, we want 3 sig figs. So our answer should be 56.4 joules. I like to use joules more often than I use Newton meters. And again, this is a positive number, so let's just include a little positive there. And that is our final answer. So the box gained 56.4 joules of energy. There was a transfer of 56.4 joules of energy. There was that much work done on it. Now, if the toy is moving at a constant velocity, how much work is done by friction? All right. So if the toy is moving at a constant velocity, let's take a closer look at that. What does constant velocity mean? Constant velocity means that there's no acceleration. If there's no acceleration, that means that the net force is equal to, you got it, 0. If F net is equal to 0, then that means the force of friction, which was maybe acting in this direction, right? And we had Fx acting in this direction. That means that they're equal and opposite. Ff is equal to negative Fx. They're in the opposite direction, but they're equal. So keeping that in mind, then that would mean that Ff is equal to negative 10 cos 20 degrees. It's the exact same, it's just in the negative direction. So plugging this into our formula, all we end up getting is the work is equal to the force of friction multiplied by delta dx. Well, the force of friction was just negative 10 cos of 20 degrees multiplied by delta dx, 6.00. And what we end up getting is that the work is equal to negative 56.4 joules. So if that object is not accelerating, that means that the energy gained because of the movement is equal and opposite to the energy lost because of friction. So they're equal and opposite, canceling each other out. Now, here's a little tricky one. How much work is done by gravity in this scenario? And this is kind of counterintuitive because if you're holding an object up and moving horizontally, so say you're holding like groceries or something for, after a visit to the grocery store, and you're walking around, it feels like you're doing a lot of work, but you're only doing work in the horizontal direction. You're actually not doing any work in the y-axis. You're not moving them up or down. Because if I take a look at, let's do this. Let's call this work due to friction. Let's give it a little subscript. I'm going to give this one a subscript of G, the work due to gravity. How much work is done by gravity? Well, has to be in the same direction as the displacement, right? So that means that we're looking in the y direction. So Fg delta dy. Is this object moving up or down though? No, right? No y movement. So that means that it's going to be 0. So what we're going to get is Fg is mg, we knew that already, times 0. And we get an answer of 0 joules. So the work done by gravity is 0 if there's no movement in the in the up or the positive or negative y directions. Now this last section here is force position graphs. So a position on the x-axis and force on the y-axis. We're doing a graph representing the relationship between force and position. This gives us work. We get work by calculating the area under a force position graph. This is very similar to being able to find the displacement by calculating the area underneath a velocity time graph, right? That moving backwards idea. Being able to find the velocity by calculating the area, the change in velocity by calculating the area underneath the acceleration time graph. So using force position graphs, we can find the area underneath the graph, and that will give us the work done. So for this graph here, I have an object that we're increasing the force while changing its position, and then we have a constant force applied for the next increasing position of another 2 meters. So what I'm going to do is I'm just going to separate these two sections. I've got section number 1 there, and then section number 2 here, and all we need to do is calculate the area. So work, oops, you know what, I'm going to use a different color because let's use green. Because I'm using blue and red here for my actual areas. So work is equal to the area under the graph. So work is equal to the area under the triangle, which is base times height divided by 2. That's our area for a triangle. Okay, plus the area of the rectangle here, which is just base times height of the red rectangle. So work is equal to, okay, let's take a look at what the base and the height are here. The base is 2. The height is 4 divided by 2. And the base here is another 2, right? 2 to 4. And the height goes all the way up to 6. So in our heads, 2 times 4 divided by 2, that's just 4, plus 2 times 6, which is 12. That gives us 16 joules. And that's a positive number. 16 joules of work done. All right. So you have got some practice problems in your note booklet. You've got 8 of them on the next or on the corresponding page in your homework booklet titled Work. You can get started on those. I'll give you some time to do those and to work on ogre number 3 if you haven't submitted it yet. Thank you for watching. Let me know if you have any questions or if anything in here didn't make sense, or even if I made a mistake somewhere. I would appreciate it. All right, we'll talk to you soon.